Feels like, yeah, like a Thursday. It feels like a Thursday.
What? Okay, so let's okay. So we ended last time with this example of a superposition. So basically second order equation, same idea as a first order equation, any linear differential equation, even with non-constant coefficients. So long as it's linear, which means like the unknown solution x prime, so the unknown solution and its derivatives all show up linearly to a power of one. You can use superposition. And so it's like a 2-in-1 problem. We have a sinusoidal and exponential term. And you have to be careful. It's probably a good idea to solve them separately. The sinusoidal term ended up giving you, of course, your particular solution form will be both the a cosine of t and the b sine of t, which has no terms that match with the homogeneous. However, the e to the t did have, well, basically it matched exactly the second homogeneous solution. So there was no hope of this being able to satisfy this differential equation with the e to the negative t on the right-hand side. So we had to multiply by t, but only this one gets multiplied by t. The sine of t, the particular solution for that one doesn't get multiplied by t. So only the term that gets, that has terms that conflict get multiplied by t. And then I think I promised, oh yeah, and I went ahead and solved so we got this up to here last time, which is the first particular solution plus the second particular solution plus the homogeneous solution. And then you find C1 and C2 by applying the initial conditions, which there is one here and another one on the derivative. And I just wrote it out here. You get C1 and C2 is equal to -1 and +2 by just like applying these two conditions. It just requires you to, the first one just says x is equal to 1 whenever t is equal to 0. And so because, their sine of t is 0 and t times e to the t will be 0 because t is going to 0, you just have e to the 0 and e to the 0 for the C1 and C2, which just is 1. So it's C1 and C2 added together equals 1. The derivative condition, which is this red one, requires you to take the derivative of your general solution, which requires just the product rule for this term right here. This orange term right here will require a product rule. It turns out to be this after you do that. And then you plug in 0 for all your t's, and then the x prime is the left-hand side here has to equal 2. And you'll get this, and you just have to, I mean, here I guess I did elimination where I said like this orange expression and this red one, if you add them together, the C1s would cancel, and then you get C2, and then you go back in and plug in what you use the C2 that you got to plug into the first equation to get C1. Okay, so I went ahead and wrote that out and posted it just because that process should not be new. But I guess I'll go back and I think I said I was gonna look at this one. This one, I guess I should have put it in the after the problem we just did, because this is kind of like a superposition, because you have these two sinusoidal functions on the right-hand side. And I just wanted to point out that there's some kind of shortcut that you can notice when you have two sinusoidal functions of a certain form. So of course there's two right-hand sides, and then you're just going to say, well, there's going to be a particular solution associated with the first one. The first one is going to be equal to, this is t times sine of t, so you have to build a general first degree polynomial, so a naught a1t times cosine of t plus the b naught plus b1t times the sine of t, because it's a first degree polynomial multiplied to a sinusoidal. The other particular solution, which is associated with the red one, is going to be just a constant because it's cosine of t. And so it's just going to be, I'll just use a cosine of t plus b sine of t. And I'm being careful, and you should also on your homeworks and stuff to make sure that all your coefficients are distinct. So these have this is a naught and a1, and this is b naught and b1, whereas this is a and b without the subscript. So in general, all these coefficients may not necessarily equal each other, so you want to make them all distinct. And there's like a lot of letters you can use, A, B, C, D, F, G, all the way up to Z. So, if you wanted to step up letters, you can do that. So these are your two particular sub-solutions coming from the right-hand side. And of course, and we're not going to actually solve for these coefficients, but I'm just going to say your particular solution due to superposition will equal the first particular solution plus the second particular solution. And I'll use colors. So this one is my orange one, and this one's my red one. And then all I'm going to do is just use what we just set up there. So you just have, this is your first particular solution. And then maybe I'll just move this down here and then say this is added to this is the second particular solution. And what I'm going to notice here is that you can combine, so there's like two cosine terms. So there's like this cosine term and this cosine term. And then there's two sine terms. It's this one right here, this one. And so I'll just like consolidate like, so there's like the cosine term that comes, so I'll just use blue just to say that these underlined in blue end up being A naught plus A plus A1t times cosine of t. So that's just saying, if I distributed this out and then this is right here, but then I basically, factored out the cosine again, then no, that's what you'll get. And then you get plus, I'll use green for the ones that are underlined in green, B naught plus B plus B1t sine of t. And here you have two coefficients that are constants, A naught and A naught and just A plus A1t. I mean, you could just leave them like this, but you could just also say that essentially you have these two constants that are added together that are some coefficient that we are going to find, but you could just say this is just like my new A naught. And similarly, you could say this is like my new B naught. Because when in the process of plugging it in, you'll have like basically cosine terms on the left that are going to have like A naught plus A times cosine of t, which is going to be like your constant multiplied by cosine. And then there's like a constant multiplied by sine, but all of them is going to have A naught plus A and B naught plus B. And those are going to have to exactly match all your constant terms on the right. And it really you have an additional freedom that you don't really need, because basically this is just going to be like together going to be another, it's just going to combine to be one of the constant terms on the right. So you could do a problem like this and you'll find out that it would have been fine if you had just rewritten these as just another constant A naught. This one you can't. This one's A1t and B1t is attached to the t, so you can't absorb it into the other two right here. So this means that you're left with actually it's just going to be exactly, let me just write this, so it'll just be A naught, because once you redefine that, it becomes this cosine of t plus B naught plus B1t sine of t. And this actually is exactly the same as this orange up here. So I'll just say these are the same. These are the same. So what this means is, so I'll just underline in purple, what we just did is we just redefined these two as combined them as another undetermined coefficient A naught and B naught. And so what it means here is that if you have the same sinusoidal function, which means that the argument is the same, so sine of t, cosine of t, then you could do superposition where you build each of them and then add them together, but it would be the same as if you just took the particular solution with the higher degree polynomial multiplied to it. So this is why I say superposition for sum of multiplied polynomials. You can always just write the particular solution of the sinusoidal term that's multiplied by the higher degree polynomial. This is just a shortcut. If you wanted to do this, it's fine. If you don't and you just want to write them separately and then add them, that's also fine, yes.
So the shortcut is like valid when we're dealing with multiple sinusoidal functions.
Yes, and they have to be the same sinusoidal function. So like you like for instance, if like let me see here. Can we do it? Let me just write it down here and say so let's see, argument has to be the same. Let me see here. Argument to the sinusoidal has to be the same. So argument of sinusoidal functions need to be the same. So cannot do it for like what we have sine of t here. Okay, so cannot do it for t sine of t plus cosine of 2t. This won't work because cosine of 2t, you'll have xp2 that has a cosine of 2t and b sine of 2t, and this combining will not work because those are going to be distinct terms. And so you cannot do it because this one's got a different argument. Now, had you had, let's say, hypothetically, that this cosine term had a t cubed in front of it, then your particular solution will end up being using this shortcut, just the second particular solution. And that second particular solution will be a0 plus a1 t plus a2 t squared plus a3 t cubed cosine of t plus b0 b1 t b2 t squared plus b3 t cubed sine of t. That's if you hypothetically had a t cubed, then this one will be the trig term with the higher degree polynomial. And so you could get away with just using that one only, or you could just add them together. But the idea is there's going to be some combining of coefficients that happen that allow you to have gotten away with just using the polynomial, using the trig term with the higher degree polynomial. And of course, if this, for instance, if this cosine term, let's say, had like instead of t cubed, or maybe in addition to t cubed, it had an e to the t here. I'll just say if e to the t here, then cannot do shortcut. You'll have to build that separately. It's only if you have a polynomial times this sine. So I guess you could have like e to the t on this one, and if you had e to the t on this one, then you could just get away with maybe just using the higher degree polynomial one. But that's just you know, this is just it's just a, you don't have to do this, but if you wanted to save yourself time, this is a pattern that we can use for when you have a sinusoidal, two sinusoidal forcing functions with one having some polynomial that is higher degree than the other one. But you could always still not use it and just have two separate particular solutions and add them together. It's just I mean, it's not a lot of work, I guess, if they don't ask you to solve for the coefficients, but if you were solving for the coefficients, it's more efficient maybe because you're reducing the number of coefficients you have to solve for. So that was, I skipped that because I thought it would kind of be distracting at the time because we didn't even talk about superposition. So now that we did do that example for superposition, I thought it'd be fine to go back and mention that little shortcut that comes from the superposition. So that's 2.6. So what we've done is 2.4, I think, was solving homogeneous solutions for second order, which was like the characteristic equation. Then 2.6 was non-homogeneous, where we look at the right-hand side. There's all these different cases, but despite all these different cases, we still have very limited kinds of right-hand side. So we can't just do something like this on the right-hand side. And also all the coefficients in front of our x and x prime and x double prime have been constant. And these a non-constant coefficient and more exotic forcing functions we'll cover later. But for now, this is all we've done is just constant coefficient with sinusoidal, exponential, polynomial on the right-hand side, or some products of those. And so it turns out that's enough for us to solve a variety of application problems. So we're going to jump into applications. So you might have noticed that I went from 2.4 to 2.6, skipped 2.5, but we're going to come back to 2.5 now because I just thought it would be nice to get rid of all, get done with all the math and then come back to applications. And this way we'll just do 2.5 and then I think we'll do 2.7 right away together rather than have 2.6 sandwiched between those two. So the classic application of second order equations comes from this Newton's second law. So F equals ma describes motion of a bunch of objects. So anything like planets to rockets to, any object that's in motion is generally described by force equals ma. And force, F is force, m is the mass, and a is acceleration. We all know acceleration is the same thing as x double prime if x is the position, right? So if x is the position function, then its second derivative is acceleration. And that's a second order equation in x. So you can shove this, we're used to the convention, right? So F equals ma becomes F equals m times x double prime. And then I'm just flipping the equation so that we're used to seeing x double prime on the left. So I'm just doing that. So this is the same as mx double prime equals F. And F is like your right-hand side in this case. And you could, I guess this is where you can think, you can appreciate why we call it the forcing function, because it's the force that's on the right-hand side of this Newton's second law. And so this describes where the position of the body, or the mass of the body is as a function of time. And so like we're going to do a bunch of problems related to using this equation with different kinds of forces involved. So if you have like a horizontal spring mass system where you're like having a spring attached to something and then you stretch the spring out and then you release it, there is a force acting on this block. And the force, there are a couple of forces, but obviously the main force that's acting on it is the spring. There's a spring force. The spring, as you stretch this, is going to want to pull it back in. And that's called the spring force. There's also friction, you could say, from the table and things, but let's just assume that maybe there is just a lot of oil on this table. So we'll initially assume there's no friction, although we'll put it in later. We'll put friction in later. But let's say the only force that's acting on this is the spring force that's pulling it in. And you'll imagine that it'll just like, well, if you don't have friction, it turns out that this, if you pull it out and let it go, it'll keep oscillating back and forth forever. The only reason it would stop in reality is because of friction. But if there was no friction, and I guess it was in a vacuum with no air resistance, then it'll just oscillate back and forth forever. And that's what we'll assume first. It's called, it's the case where you have simple harmonic motion. This corresponds to no damping. There's going to be a delta term that we'll introduce later. And so here it doesn't show up in the equations because we're assuming delta is equal to 0. And damping is any kind of resistive force. So friction is damping, air resistance is damping. When we cover electrical circuits, then there are resistors in the circuit, and those would resist electrical, like motion of electrons. Those are going to be those are all damping. Damping is just something that damps the motion. So let's look at a horizontal coordinate system where x equals 0 corresponds to the natural length of the spring. So if you just like let the spring be itself, it's going to have a certain length to it. And we're just going to say like that attached to the wall, and however far that goes, the natural length that's not stretched or compressed is going to be your origin. X is equal to 0 position. And then we say x is positive to the right. So that means that if you pull and stretch it, in the picture that's given here to the right, then you'll get you'll have positive. So basically it's like x is greater than 0 going in this direction. So stretching is positive. and then it's negative if you like moved in the left direction. So let's first consider the total force that's acting on this box to be just the spring force. So I just say here, it's just the spring force. And there's a subscript S here for the spring force, Fs. Because I'm gonna, well, you see that here too, right? Fs. Because there's gonna be all kinds of other forces we're gonna introduce into the system, and it'll be good to keep track of what force is what. So we're gonna just use that convention that the spring force is just F sub S. So there's by Hooke's law, it's like a law that says that the force exerted by the spring is going to be proportional to the distance the spring is stretched or compressed. So the further you stretch the spring, the more the spring is going to try to pull it in. So like, let's do an example of this. So suppose you stretch the, let's say that you took this thing and then you pulled the box from the 0 position to the x equals 2 position. So it's like pulled out here. So you pull it out all the way. So let's say you pulled it out to this position. There's going to be a spring force that's going to act in which direction, left or right? If you pull intuitively, right, it's going to act in the left direction. It's going to want to pull it back in, right? And so that's why we have a negative, because it's in the opposite direction from what you did. So like, let's say your x right here, right? So if you're 2, then that means your x is equal to positive 2. And you're going to end up having your spring force will equal negative 2k, assuming k is some positive. So we'll just assume k is some positive number. So I'll just, that's right here. So I'll just say F. It's called a positive stiffness constant. It just measures how stiff your spring is. So the stiffer your spring, the higher your K. And so when you pull this out to a position of 2, you're going to have a spring force moving in the negative direction. That means it's going to pull in the left direction, because remember, x greater than 0 is to the right. So when you have a negative sign, that's pulling to the left. And it's going to be equal to negative 2 times k. And if your spring is really, really stiff, your k is like 100, then it'll be a force of like 200 newtons to the left. But if your spring is really not very stiff, like maybe just a stiffness constant of 2, then it would just pull in the negative by 4, And so that's the stiffness constant, and you see the sign, and it's proportional. So like hypothetically, if you took this spring, this box, and you pulled it out to x is equal to 4, that means you pulled it out to here, you would expect the spring force to be bigger or smaller? Bigger, right? Because the more you stretch it, the more force, and you can test this. I mean, if you happen to find a spring, and if you just like pulled it a little bit versus if you pulled it a lot, you're going to feel the force of the spring. I guess if you like were really strong and pulled it too far, then you're going to you're going to distort the spring. But assuming that you don't go that far, you'll notice that so what happens when x is equal to 4, then this x is going to equal 4, which is going to give you a spring force that's going to equal negative 4 times the k. Whatever the k is, it will be more because there's a 4 multiplied to it rather than a 2 that's multiplied. And if you pull that out to x is equal to 10, then that means that you're just going to, so that's what it means to be proportional to the distance the spring is stretched or compressed. So if you actually took this and compressed it, so let's say if you moved it inwards and say this position here, just say here, and then this is like x is equal to negative 2. It's negative 2 because we're using the convention that the right stretching is positive. So if you pulled it to negative 2, that means that your x here will equal negative 2. Well, it's going to become negative times negative 2 times k. So your spring force will equal just 2k. 2k positive, because of this extra negative sign that's in this x plus this multiplied by this extra negative, this negative sign in the front. This is a 2k, which means that your spring force is, if you had compressed it, will equal to 2 times k in the positive direction. Right? So it's going to push it out back to its equilibrium position. So that's why there's a negative sign, because the spring force acts opposite to the sign of x. And so if, you know, there are different conventions for what K is. So basically it's supposed to make sure the units work properly. So if the force is in newtons and X is in meters, then K will have units of kilograms per second squared. And sometimes they use dynes, and so that's fine. So if we only consider the spring force, no other forces, no friction or anything, the total force, right? So let's go back up to this equation up here, this one right here, mx double prime equals F. That's our, you know, Newton's second law. So there's a bunch of other forces that we'll introduce, but this is what we start with. We have this mx double prime equals F. But if we only have spring force, then the only thing we have is just this F of S, right? That's the only thing we're gonna have. But F of S equals this, right? So F of S is equal to negative kx, which we justified by doing a bunch of these cases and noticing that it makes sense to be proportional to the distance that it's compressed or stretched, and it always acts in the opposite direction. So that's why I'm just saying F of S is equal to negative kx. Well, mx double prime equals negative kx, that I can write in standard form by shoving, like we like to have all my x's onto the left, right? And so really this is just mx double prime plus kx once you move this to the left equals 0. It's a linear second order homogeneous constant coefficient differential equation. We know how to solve these. In fact, we knew this one's like easier than what we just did because it's homogeneous. So that's why the book actually has this section right after 2.4, because you really only need 2.4 to be able to solve these types of equations. Now, if we introduce more forces, you're going to maybe have a non-homogeneous differential equation. And that's why that's 2.7. That comes after 2.6, which is what we just covered. But I'm just doing 2.4 and 2.6 together so we get all the math done, but we'll do applications only for the next week. So consider a spring mass system without damping. Again, we're just like, it's super well oiled. This never stops if you had let it go. A mass of 3 grams, the spring constant K equal to 48 grams per second squared. The mass is displaced by 1 centimeter to the left. So there's this equilibrium position, which is, so they like to use L as the natural length of the spring. And so this is looking like, you know, this L would have been X is equal to 0 position. But they imagine you compressed it by pushing it in. And then you do a gentle nudge to the right before you let go of it so that it has an initial velocity of 4 centimeters to the right. So you could have just let go, but you might have just like put in an initial velocity into this as you let go. You want to know what's the position as a function of time. So can you model the position of this oscillating mass as a function of time? The only force that's acting on it is the spring force. And we can, because it's basically the differential equation we just had before. It's this right here. So I'll just, well, you could see it. So I'll just say here, you see this mx double prime kx. So I'll just write it down here. This is all we're going to have for this problem because we don't have any other forces but the spring. And to give you all the information you need, because they tell you the mass is 3, and they tell you the spring constant is 48. And that's all you solve is this differential equation. So this is like a homogeneous second order differential equation. You could divide everything by 3. You're allowed to do something to everything if you do it to every single term. So if you divide everything by 3, then this just becomes 48 divided by 3 is 16. And so you have this. You say your yes.
Why is it? Oh, wait, no. So when we're doing this spring constant K, it's always positive. Right?
Yeah, it's always positive. They use a spring constant, it's positive. Otherwise, it'll really mess up this convention of like having a negative in the front here. Because then you're going to have potentially a spring that, like if you actually stretched it, so if you move this out to here, you'd expect that it'll try to pull it back in, but then you're going to have a situation where it like tries to pull it back out, which makes no sense. So this is going to always be positive, this K. And so this characteristic equation would be r squared plus 16. is equal to 0, which of course you can solve and say r squared is equal to negative 16, which means that r is equal to plus or minus 4i. And so you'll have, in this case, complex roots. It's pure imaginary, like you can tell because there's no alpha, no real part, but the beta is equal to 4. And we know from before how these solutions are like. The real solution will end up being C1 e to the alpha t, but that's just 1 because e to the 0. And then it would be cosine of 4t plus C2 sine of 4t. So this is your solution to this differential equation. It's just a homogeneous, so that's it. You don't have a particular or anything because this is just 0 on the right-hand side. But this does give you some initial conditions. So it's telling you that the mass is displaced by 1 centimeter to the left of the equilibrium position. And it's nudged so that it has an initial velocity of 4 centimeters to the right. So what are these statements saying? Mass is displaced by 1 centimeter to the left of the equilibrium position. So at the very beginning, x of 0 is equal to what? Good, negative 1, because it's to the left, right? And then the velocity is 4 centimeters to the right. So x prime at the initial time is equal to what? Just positive 4 because it's nudged to the right. Now, if it was nudged to the left, it would be negative 4 because the direction, right, is using this convention that this is positive is this way. So that's the only two conditions. So you know we're going to have to take the derivative of this because the purple condition requires is a derivative condition. So we're going to say x prime of t is equal to negative c, well, got to do the chain rule, sine of 4t plus 4c2 cosine 4t. So that's just making sure that I have the derivative on hand because this orange condition is simple because it doesn't require you computing the derivative. So I'll just say x of 0 is equal to negative 1. That just means that negative 1 is equal to plugging in 0 for t means that sine of t for t will go away. So you just have c1 because cosine of 0 is also 1. So you just get this. So automatically get the c1 right away. And then you have your derivative condition, which is like x prime of 0 is equal to 4. That means that your 4 is equal to all of these with 0. So, sorry, I forgot to put a C1 here. So this goes away because sine of 0 is 0, and then you just have 4 C2. So this just means that C2 is equal to. So that's the C2. And then you just have, with that, you can find the real full solution. It's just going to equal x of t is equal to C1 is equal to negative cosine of 4t plus C2 is 1. So it'd be sine of 4t. And that's exactly what's being graphed here. This is describing the motion of the mass as a function of time. If you plug in, okay, so I'll just say this is the position in centimeters because all the units you see in this problem are centimeters. So this is going to give you the position in centimeters where x of 0 is the natural length of the spring. So if you plugged in 0 into this, sine of 0 is 0, cosine of 0 is 1, you'll get negative 1, and that's why you see here your initial, I'll just make it orange and say, you see here, actually, I'll just do this. You see how it does indeed show you that initially this position is at -1, which means that it's it's 1 centimeter to the left of the equilibrium position, which is the length of the natural length of the spring. And then it's, I mean, if you were to look at the tangent line here, you should see that the tangent line will have a slope of 4 because you want to have the x prime of 0 to equal 4, and that'll be true. You could check that by just taking the derivative of this, but this is just saying that there's a slope that's 4. Let me just think of it as, well, I should probably. So like there's a slope of 4 here. And so that describes this. What's going to happen is that you're compressed. So the spring is going to want, and not only are you compressed, you've nudged it to the right too. So you're not going to, you'd expect that this thing is going to move to the right. It's going to move to the right until it hits the natural length of the spring, but it doesn't stop because, you know, there's still force that's momentum in this object that's going to pull it out. And it's going to go all the way out to here. There's a 2 here, so I guess it's like not going to stretch more than 2 centimeters from the equilibrium position. But as soon as it goes out there, well, immediately when it passes the L position, which is the x equals 0 position, the spring force is now acting in the other direction. Because as soon as it passed that position, now the spring is like, oh, you're stretching me, so I'm going to try to pull you back. And it's going to be proportional to how far you made it past this equilibrium position. And so that's why it comes back. And then because there's no friction, it just shoots back past the equilibrium position. And now it's compressed again. And then the spring is going to be like, I want to stretch. So it's going to push you back out. And it's just going to keep doing this forever. And that's why it's just going to oscillate and never, ever stop, assuming you have no friction. And that's how it'll just continue forever. And that's called simple harmonic motion. So that's how you would describe the position of this. But you might want to be able to extract more information by looking at this. Can you tell me what's the amplitude of your oscillation? So how far does it actually go out before it comes back? What's the maximum stretching and compressing that you'll see this object do to the spring? It's not immediately clear, like by looking at this, what the amplitude is. You might think it's 1, but it's actually not 1. Because, well, I guess maybe from the graph you can see that 1 would have been like halfway. So it's a little bit, because this is a 2 here. So it's like 1 probably would have been here. It's a little bit higher than 1 is the amplitude, but you wouldn't be able to tell just by looking at this immediately. You might also want to know what's the period or frequency of your oscillations. And also that's not clear as easily by just looking at this solution here. So that's why people like to rewrite this in so-called amplitude phase form. So, this helps identify amplitude and phase, but also allows you to graph it more easily if you didn't happen to not have a graphing calculator so like if you just had this, it's hard to tell what the graph of like negative cosine of 4t plus sine of 4t would be. But if you can write it in a form where it's a single trig function, then it could be easier to see how to graph this, because the idea is that you might have these 2 trig functions, this cosine one and this sine one, combine. How does this combine into a single, let's say, cosine function of this form? If you have it written in this form, then like there's something immediate that you can say about this. So if you're able to rewrite something that's written as 2 trig functions like this into a single trig function like this, what would be, like, from looking at this expression on the right, what is the amplitude? Good. Yeah, exactly. So this is like the amplitude. And so the question is, what is that R? And then it turns out that this phi here is the phase angle. And this is information that we wouldn't be able to see from this directly, but we could if we were able to successfully rewrite it in this form. So it's just a bunch of trig to be able to write it in this form. The thing I'm going to use is the cosine subtraction formula. So what I'm going to say is there a way for me to rewrite this left-hand side into this? And if we did, what must have been our R and phi for that to be true? So what I'll note here is that suppose you have, what we start with is x of t is equal to the C1 cosine of omega naught t plus C2 sine of omega naught t. That's what we start with. Let's use so I'm just going to use the cosine subtraction formula on this expression right here. So this is just saying, I'll just write it here and say r cosine of omega naught t minus phi. Okay, this is like the same as r times. I'm going to do some colors here. So I'll just say like this is orange. That shows up here. And that shows up here. And then I'll use blue. Say this shows up here. Shows up here. So let's do the same thing down here. So this is like our A, right? And this is like our B. This is like our orange. So you have a so what we have on the right-hand side is just a cosine of two things that are subtracted together. And this formula says that I can rewrite it as this expansion here. So if our orange is now this, that means that we have cosine of omega naught t times cosine of phi plus sine of omega naught t sine of phi. And I'll use the colors. So this is blue, this is blue. This is orange. This is orange. So all I did was I took this right-hand side and expanded it using this this cosine subtraction formula. There's an r in the front, so I'm just like saying it's r times the entire thing of this being expanded. And so we have the left-hand side is this equals the right-hand side is this, and we're trying to force this to happen. We're trying to find capital R and phi that will make this true. And that'll give us the proper R and the phi that would have taken this left-hand side and rewrote it in a single cosine function. So what we have is basically, this was our left-hand side, which is the original form of our solution, equals this. And I'll just get rid of all these colors and just, and then whoops, and then I'll just distribute the R to each of these. So it's going to look like R times this, and then I'll just move this over and just say this is R. So now I'm going to try to find R and phi that will make this true. It's going to be just matching. So I'm going to say this cosine, and there's a bunch of cosines here. And then I'm going to say this right here. It's a sine term with all these sine terms. So in order for C1 cosine of omega t to equal R cosine of omega t cosine of phi, this means that C1 has to have equaled what? Just R, not just R, right? Yes. That's the only way you're going to get this to be true. And then the other one is this C2 has to equal what? Yeah. So we're just saying, okay, we have something written in this form, you know, two sinusoidal functions, kind of like up here, right? I mean, in this problem, omega naught was 4, and then C1 is -1, and C2 is +1. And we're just saying, well, let's say we hypothetically want this to look like this. What must have our capital R and phi been? you use cosine subtraction formula to expand. That way you can get terms to resemble things on the left like this, and then you match these to say, well, that means that C1 and C2 must have been these right here. And what do you notice? Like, have you ever seen something like, something is equal to R cosine of phi and the other one's equal to R sine of phi before? What does that remind you of? Polar coordinates, exactly. So notice that that the R phi that we are trying to find is polar coordinates of the Cartesian coordinates C1, comma C2. So C1 acts like your X and C2 acts like your Y. And the polar coordinate formula says that you can use the, basically you can find the C1, if you had polar coordinates says this. So basically you'll have a coordinate system where it's like this point right here, C1, comma C2. You could also think of this as the angle phi and the distance r. And if you remember like your trig, so it's going to be like, what is this? Cosine of phi is equal to adjacent. So this is C1, adjacent over hypotenuse. So therefore C1 is equal to R cosine of phi. So R is the distance between this origin to your point. So like for the problem we just had, we had that C1, comma C2 was equal to -1, comma 1, right? So that's what we had. C1 is -1 and C2 is +1. So what must have our R been?
C1 squared plus C2 squared.
Yeah. Which is going to equal square root of 2. So the amplitude of our oscillations is square root of 2, because we said that R is the amplitude. That's not immediately obvious from looking at this, right? Because it's negative cosine of 4t plus sine of 4t. But the C1 is -1 and C2 is +1. And you just do those, you just interpret those as the Cartesian coordinates, and you just find the modulus, the magnitude of your polar, and that's going to give you your amplitude of your oscillations. And we'll do the phase angle and everything and talk about this a little bit more, but we don't have time today. So, okay.